lecture, and as usual I like to recall what we did last time. We did quite a lot if you think of it. We introduced several new methods, at least 3 if I count correctly. One was called the Gauss-Newton method, the other was called the Leeuwenberg-Marquardt method, and the third one was called the exact Newton's method. And they will actually all fall into the same class of what we call Newton-type methods. And I think instead of summarizing them, I will come back to them in this lecture by classifying them along the lines of our new language. And the other thing that we did, where we defined convergence rates. So you remember there were these Q convergence rates, there are the R convergence rates. The best of all the convergence rates we looked at was Q quadratically, yeah, which is I will not recall all the definitions, but maybe this one I do. So recall what we mean here is actually that the distance of some point of a sequence that should converge to a point x star would shrink quadratically in the sense that there is a constant, and then here we have the distance of the previous iterate but squared in any norm, the main point is when this is small, then this is much smaller and getting quadratically smaller, so you get actually extremely fast convergence once you are close to the solution. So that was Q quadratical convergence, and then there are other convergence rates. We had also the superlinear, but I don't put the definitions. And also we had the linear convergence rate. And we didn't yet specify which of our methods does have which of these convergence rates, but we will come back to that today. So we will actually analyze, using a bit of analysis, the convergence properties of the Newton-type methods. But before we do that, I want to frame it by recalling basically what we did last time, but already reordering the language. So what we call a Newton-type method for optimization, is the following. It is an iteration where we would just say that a new iterate x I or k plus 1 is equal to the old iterate, and then we do something where we remember there was always this general form with a minus sign, and then there was something multiplied with a gradient. Yeah? And what we did here was we added some metrics, and I don't specify this matrix now, but I just say this is some matrix which should be, in the perfect case, invertible, of course, so otherwise I cannot write this even. But it should also, in the perfect case, be positive definite. But let me just discuss it a bit. With bk element in Rn cross n, invertible, that's the minimum thing that we need, otherwise we couldn't even write down this formula. Then we call this already a Newton-type method for optimization. Type method for, I should say, unconstrained optimization. Of course, we are in the part on unconstrained optimization. But that's the name that we give to any method of this, and we didn't specify now what these matrices are. But what I want to say already is that we can give a second interpretation. That was one way. You remember this could be the exact Hessian if we have the exact Newton's method. It could be something else in the case of this Gauss-Newton method. But we had also the model interpretation. We could also say in the second interpretation, we would also, in the second interpretation, we would say xk plus 1 is equal to xk plus some step pk. And the step pk is obtained by solving an optimization problem, which is an approximation of the original one which we call mk, xk plus p. So it's a model for the objective. And you remember, if we set for this model mk, xk plus p, this Taylor series, the first order Taylor series, plus a quadratic term which is actually using this matrix P, bk, then by setting this gradient to 0 and assuming positive definiteness, then this would be actually the necessary optimality condition, and we come back to that form. Yeah? So the second interpretation is this interpretation where we say we have a step, and the step is actually obtained by the argument that minimizes a model, and this argument that minimizes the model that we have is actually a kind of Taylor series but with some quadratic term, and this is only possible if this bk is positive definite, which is the thing that we would really like to have, and I will explain in a minute why. Do you remember this, or should I derive it again? So why this second interpretation is leading to exactly the same iteration? No, not necessary. Not, right? Good. So let me just say one word, which is quite interesting, because what we, if you think of this this fact, what we do in optimization is actually we are in the dark in a space where we want to find the minimum. Yeah? So in some sense, you could just say I'm walking in the Swiss mountains, for example. I don't know if I gave you that example already. I don't think so, right? And it's night, yeah. And you know, in the valley there is your bed, yeah, the hotel where you have already a bed, yeah? And you want to arrive at the valley, and you don't have anything apart from local information because you can't see. And in this case, we have basically a two-dimensional optimization landscape, and you want to go downhill. And the most logical thing that you would do in this context is probably try to go downhill. Yeah? Whenever you go upwards, you think this cannot be the right thing, right? And this is exactly how many optimization algorithms will actually work. And so the idea of going downhill is extremely important in unconstrained optimization, because it will make sure that you always make some progress, in sense of decreasing the altitude, so to say. Yeah? And it's not necessarily the shortest way, as you might imagine, right? So it could be that going downhill leads you through a very long valley until you are there, but while going above the mountain would lead you much faster to the desired location. But then you are not sure. And because it's dark, you rather go downhill, right? And so there is one interesting thing that I want to note. If this property holds, then actually the direction is already a downhill direction. It doesn't mean that the next iterate will be better, but at least it goes into a direction where your objective is going down. And this is some lemma that I want to prove very briefly, and it's extremely easy. But I just want to say what this P is. Yeah? Basically here I didn't derive it, but pk is of course minus bk to the minus 1 nabla f of xk. So that is what you get from minimizing this model. That is the step that you get. Yeah? So this explicitly solved gives this solution. And now this lemma says if the matrix is positive definite, then pk equals this thing, minus bk to the minus 1 nabla f of xk is a descent direction. You remember what is a descent direction? It was a direction which, in which direction your derivative is actually pointing downwards. Yeah, the first order Taylor series. So descent direction means actually that nabla f of xk transpose p, that this should be a negative number. So let's just look what it is. So we have this thing here. So we will insert it and we get the minus sign, xk transpose bk to the minus 1 nabla f of xk. And you immediately see, because it's a positive definite matrix, its inverse is also positive definite. It's multiplied from left and right with the same vector, and there's a minus sign. So this is positive with a minus sign. It's negative. and it's smaller than 0 if nabla f of xk is not equal to 0 and otherwise it is 0. Yeah, so it's a descent direction. This is actually part of the statement if, right? So technical detail. If you are at 0, then you will not go down. Okay, so in that sense, not only this quadratic model interpretation is a nice thing about positive definiteness, but also the fact that we have a descent direction is a good thing. So at least the next step would first lead us downwards. Maybe it's actually too long. That's a question that we will later do, right? So if you are in a valley and you make a too big step, then you might be on the other side of the hill already, right? So that's not very useful. But if you have already these descent directions, you are in good shape because you, if necessary, you could make your step short. And if you make it short enough, you will go downhill for sure. That's the intuition behind a descent direction. But before we go on, I want to already point out what will be the main 2 points that we have to discuss. So that's actually questions we will address in the next chapters. Yeah, one is so 2 questions. The first question is if you start somewhere far from your solution, it turns out that this Newton method will sometimes not converge. You might not have even positive definiteness and so on. So you need to somehow make sure that you can converge from far away solutions. So we call this globalization. So how do you make sure that your algorithm will actually globally find the next local minimum? Yeah, so it's a bit funny. We call it globalization. It has nothing to do with global optimization. It just is globalization is the first question. Globalization. And the question here is how to arrive from any x0 at a local minimum x star. Yeah? So when you are very far away. So global convergence means that you can actually start your algorithm everywhere and it will just go down, and at some point you will arrive at a local minimum. That's what we want. And this will be treated in the chapter on globalization strategies. The other question that I want to treat first, because it's a bit easier, is actually the question when you are close to the solution. Imagine that you are already very close to the valley. So you are actually on the way down the Swiss Alps. You are already somehow close to the valley. You don't see light because somehow everyone sleeps already. Let's say it's 3 o'clock in the night. Yeah? So you don't see where your house is. But then you would actually at least have an algorithm that quickly brings you back to this desired location. And so that is the question of what we call local convergence, and which is where all these local convergence rates like U quadratically and so on, they play a role at the end of your algorithm. Yeah? And it turns out that some algorithms will be even at the very end, so you're very close to the solution, but they are extremely slow and it's tedious, so you don't make much progress even though you're already in the right lane. Yeah? So the second question is the local convergence. Which is, so to say, close to x star. So when you're already close, how fast will you be? And because I promised that I actually want to summarize, I want now to bring the methods that we introduced last lecture in this framework of Newton-type optimization methods. So I want just to define the B for different methods, and we will, in the next exercise sheet, implement these methods on a simple example. But this is, in a sense, a definition. Yeah, so it's a lot of definitions, but just so that we know exactly what we talk about it. So this is what we want to talk about first in this and next chapter. So Newton-type variance. So Newton-type optimization. variance. And the only thing that I need to define is actually the B. But the first one is the Gauss-Newton method. And I introduced that last time together already with the Levenberg-Marquardt method. And you remember what we did there is actually we could apply it only to one class of problems, namely the problems where we have f of x given by 1/2 some big F of x. And I should say that whenever I write a big F, I mean a vector valued function. That's like my personal convention here. In this case, it's the sum of squared residuals. Yeah, and that could be coming from a fitting problem, but it can also come from something else. And what we already derived was that the gradient in this case is given by J x transpose F of x, where J is the Jacobian of F. But of course this you can put into the formula for the gradient. That's not the difference to before, but what is the difference to other Newton type methods is actually in the Hessian. And the Hessian here is best, I think, remembered when we look at the linear model. I mean the model interpretation, and then we can look afterwards what will be the Hessian. I think that's the most logical way to do it. And in these methods, I think it's very logical to define the model first. So the model here was actually f of x. No, I will not do it this way. I will actually do it the other way. Namely, I say, what was the model that we use? We use actually a linearization of our function inside the norm. That was the quadratic model that we get here. And we add possibly, that's what the Levenberg-Marquardt term does, some alpha k half with a penalty on the step size p. So that is the model that we use here. So we use a linear expansion of our nonlinear function. We put it in the norm, and I claim that this is actually a quadratic model, and we can easily do it by just multiplying these things out. And what we get here is actually 1/2, and then this term alone, f of xk squared, right? Then there is another term which is actually a mixed term between these two things. So that will be 1/2 times, and then we get a 2. And then here we have the j xk transpose nabla f. So this was wrong. Maybe I do it. Yeah, it's okay. It's not wrong, but I need another transpose now times p. And here I transpose. So that's the term where I multiply this j. I reordered things, j and p come together in some sense, and then they are multiplied with this f, so there is no gradient here, with this f, and that term appears twice, so that's why I have this 2 here. And then come the quadratic terms, and one quadratic term is actually coming from this thing with itself, so it will be actually p transpose j of xk transpose j of xk times p. That's from here. Now I have done the first thing, and then I add to this actually plus alpha k half p, or maybe I write it like this, p transpose p, just for fun. So now I look at this and I see, okay, that's actually very consistent with my model interpretation, because it's nothing else. If I look back at my original function, then this is actually the function value. It's a constant. It doesn't matter actually, but it's nice to have it. It's consistent. So that's the small f at xk, right? This thing is the gradient, and it comes exactly with these things. So what I have here is actually nabla f, little f at xk transpose p. So the first two terms are the same, but here comes something quadratic, p, some matrix, and with another matrix, and this, of course, I can put the alpha in the middle, and then I get plus 1/2 p, and then here I have j of xk transpose j of xk plus alpha k times the unit matrix and times p. So you agree that I collected the terms, and what we see is that we really have a specific form of a Hessian approximation, and that's the only difference to the general method, and this one is bk. Okay, so the Gauss-Newton and the Levenberg-Marquardt method, they choose a special form of Hessian, namely this Jacobian here, plus possibly a term. So for Gauss-Newton, we have just alpha k is always 0. And for Levenberg-Marquardt it would be positive, and how to choose it is another and not completely trivial question. But let's just introduce these methods. There's one thing that I want to argue already. And you remember actually that we had one method that I did not define, but maybe I should have defined it, but in this lecture notes I didn't define it, but that is the exact Newton's method, right? So what is the exact Newton's method doing? So maybe I call it, I should call it B now. Or I should call this is actually B. It would be much more logical that I started with A. Sorry for this. So I just wanted to say that for the exact Newton's method, we would just say bk is equal to the second derivative of f. That's what we did last time, but I just wanted to recall. This was one of the methods that we looked at, the exact Newton's method. We would just have the second derivative exactly evaluated. Now for the Gauss-Newton method, we have a different setup, and we just use a different b. So the question that we want to compare is actually A and B, Gauss-Newton and exact Newton. So these two things we want to compare. And I just want to do it once with you so that you get this feeling of how different is actually this matrix from the exact Hessian. Yeah? So the Gauss-Newton method is a very, very nice and very powerful method. And it has this very beautiful approximation of the Hessian matrix, which turns out to be positive definite, because that's a positive semi-definite matrix, and if you add something positive, then it's really even a bit definite matrix. So it's a very beautiful thing, but how different is it? So what we can do is actually we can compute for this case where we have f of x equals 1 over the norm of f. We can compute this, the first and the second derivative. The first one we know already actually, yeah, so we know that nabla f of x is given by this expression that I wrote, but I will write it a bit differently just so that you get this. This is actually fi of x, and these things are scalars, and we square them all. Yeah? So the derivative of this whole thing with 1/2 will be actually the sum of all these fi of x times the gradient of fi of x. And because of this 1/2, the factor 2 cancels. So that is the first derivative. And please note that I recollected these things. These are gradient vectors and these are numbers. Yeah. So what will be the second derivative? It will consist of two terms. One is where I take the second derivative of this thing that just makes the Hessians, and then there is one term which will be giving the second derivative of this thing. And together I need to assemble the derivatives so that they form a matrix of the right dimensions. So let me do this thing first. So I get here actually the gradient of this thing. It's the same thing, and then this one. And in order to make it a Hessian, I need to transpose one of them. So now this is a matrix of the right dimensions, and it contains all the partial derivatives of first order. That's what I got from here, and then I got the other thing will be actually the sum of fi of x times the Hessians of fi of x. So what you see here is a complete, just a computation of these derivatives, first and second. And what is now interesting is if you think of what was the j of x. Yeah? So that was d big F of dx. And it was a collection of all these gradients actually. df, df1 of x transpose up to nabla f m, right, of x transpose. So that's what is a Jacobian. It's the collection of all the gradients of the single components. Yeah? So each of these is one row of the Jacobian. And that means that also J times J transpose is actually given by this whole thing. So J transpose J is actually, you see this thing transposed is giving you this, and then they are all multiplied with each other, and at the end you see that it's the sum of these things. Yeah, so this is actually J transpose J, and we can go on and say that nabla square f of x is given by J x transpose J x plus the sum of fi x times nabla square fi x I from 1 to m. And we have now with these computations actually derived a similarity between the exact Hessian and that's the Gauss-Newton Hessian. And this thing is of course a difference. And in some case, or sometimes it is called the error matrix because it's the error that we make in approximating our exact Hessian with a Gauss-Newton Hessian. And now the question is, when is this error matrix actually small? I said already last time, and we will prove it today in the second hour, that if you take the exact Hessian, you get a quadratically converging method. So in principle, it's good to have the exact Hessian. On the other hand, this exact Hessian is involving second derivatives. It's expensive. It might not be positive definite, so that's also bad. And we might like this Gauss-Newton Hessian, but then we would expect that if these things are similar, then we have good convergence, and if they are not very similar, we don't have so good convergence, right? So when is this matrix small? Is this thing actually? That's the arrow, yeah. And if you look at it, it's actually consisting of two terms, and each of them can be small. Either this is small or that is small, or both are small. If one of them is 0, you're done. The good thing is that in very many cases, one of the two will be small. And let me just say what would be nice is actually if these second order terms, when are they small? When they are small, actually, when your model is nearly linear. If f of x is nearly linear. Because if it would be linear, then there is no second derivative, right? A linear function does not have a second derivative, and so if they are nearly linear, then you have small second derivatives, basically. The other thing is fi of x are small if actually the whole thing f of x is small. And this is even more exciting because this is the residual, the thing that we wanted to minimize at the end, at the beginning, right? So that's the objective function, and that means that if we have a good fit, because these are the residuals that we wanted to make these things 0, and when we have a very good fit, then the objective will be very small. In the perfect case, we have perfect fitting, and then all residuals will be 0. And then actually, if all the residuals are 0, our best objective value is achieved, 0, and this term will be vanishing completely. So we see that in the case that we have a perfect fit, the Gauss-Newton and the exact Newton Hessians even coincide. So this is something, note, for perfect, which is never the case, of course, perfect fit with 1/2 f of x star being 0, Gauss-Newton and exact Newton Hessians coincide. So that's an interesting information I wanted to share with you. And the practical conclusion is actually that this Gauss-Newton method is giving you something similar to a Newton's method if either you have nearly linear models or if you have a good fit. And of course they are multiplied with each other, so yeah, your fit can be, your fitting error can be very large when you have a very linear model and the other way around, and then your method will still work well. But we come back to that. I wanted to go into more variance, so to get these definitions actually more complete. And so now I'm actually counting one counter more than in the script. So C is now what we call the steepest descent method. So what do we here? We actually just take a unit matrix, a scaled unit matrix as this B. So we just take bk being alpha k times a unit matrix of the right dimensions. And with this one, we will actually automatically get that pk, so the step is minus 1 over alpha k times nabla f of xk. So this is again a method that I could always apply. Gauss-Newton I can only apply if I have a quadratic objective, but now I'm back at the general case. So that's the negative gradient. And if you think what the negative gradient is, it's actually the direction of the steepest descent. So this is the direction where you go the steepest downhill. That's why it has this name, steepest descent. So I just want to illustrate that with a line. So let's assume that here are the level sets of your valley, and maybe here's the place where you want to arrive, the hotel in the downhill region of your Swiss Alps or wherever. And now you are here, and the steepest descent direction is actually the gradient is always orthogonal to your level lines. That's the property of a gradient. And the steepest descent direction is actually in the negative direction. So that is the steepest descent direction. It will lead you downhill in the steepest way. It's not necessarily the fastest way to the solution, as you see already from this plot. Yeah? So ideally you would go here. But the steepest descent method is some of the variants that I wanted to share with you so that we have a quick overview of all the possibilities. It's also a Newton type method, but it uses a very, very primitive Hessian approximation. And then there are some methods which are practically very useful and which we will also program, which are called the quasi-Newton methods. In quasi-Newton, I mean, it sounds like Newton type or quasi-Newton, and sometimes the language is also a bit just mixed. In the mainstream language, which I also try to adhere to, is Newton type is this whole class of methods where we choose some matrices, and quasi-Newton methods are the ones which actually update this Hessian during the iterations based on gradient information only. So when we say quasi-Newton, then the idea is to generate bk plus 1 based on bk. So actually you always work with some approximation, which at the beginning it could be, for example, a unit matrix, and then you try to improve it and to make it more similar to the real Hessian by taking your old one and doing something with it, which is in order to get the next approximation for the next iteration. And what you use here is actually you use also knowledge of the last gradients actually, and the difference of the gradients that you got during the two iterations, and which I call now y. I will just do it in a second, and of your distance of the two steps. And I call that s. Now maybe I should call it yk and sk to be with the index. So basically, the idea is to just use somehow information that you got during your iterations by just computing the gradient and the difference actually of two gradients and the difference of two primal variables or of two variables, and to use that in some formula that should give you a better approximation of the Hessian. And so this is a whole family of methods. There exist many, but one thing that they always satisfy, or nearly always, usually, they are satisfying the following property. So phi-ing, the property that bk plus 1 times sk should be equal to yk. So that's a property that you usually make sure, and it's called the secant condition, and I will motivate it in a minute. And I will actually try to plot it and why this is a condition that makes sense. So maybe I should first say what you would assume if you have a quadratic model. Yeah? If you would have a quadratic model, so let's motivate this condition by assuming quadratic model, quadratic f of x, which could be given by something like the gradient, so C transpose x plus 1/2, and then I have here x transpose bx. Yeah? And maybe I give it a bar because it's the true b, right? So that's something that you don't know, but that you would like to know. And now if you compute the distance of wherever you are, 2 points, this thing, for this quadratic model, it will be the difference of these two gradients. But these parts are the same, so the C terms actually vanish. I mean, nabla f of x would be given by C plus bx, b bar x, right? And so now what we would expect here is actually exactly b bar times xk plus 1 minus xk. So you see, if we would have a quadratic model, then this thing is actually yk, this thing is actually sk, and it would satisfy the true the secant equation if we would have a quadratic model. And so now we assume, of course, it's approximately quadratic, and because our matrix here it's a high-dimensional object. It has n times n entries. This is a constraint on our matrix, which is actually n. It contains only n conditions because it's a vector-valued constraint. S is fixed, y is fixed, so there will be only n conditions which actually our bk plus 1 should satisfy. But these are conditions which the true matrix, if there would exist a true quadratic Hessian here, should always satisfy. But of course there is, because we have n times n conditions, possibilities for choosing these values of b, but we have only n conditions, we have freedom, and that's why there exist many different formulas, which all satisfy this condition. They satisfy also that bk plus 1 is somehow based on bk, but there are different formulas. And one of these formulas, which is the practically most often used and also very successful one, is called the BFGS formula. And that's like the prime example of a quasi-Newton method, which I want to present. It's a simple formula, the BFGS formula. And that is going back to 4 optimizers, Breuden, Fletcher, Goldfarb, and Shannon. I think, if I'm not mistaken, they all are still alive. And it was not published in one paper, but it's actually something which was discovered at the same time, and they agreed to order the names alphabetically, BFGS, and this is how mathematicians avoid conflicts, right? So we have bk plus 1, and the formula just says that you take the old one and then you modify it a bit by making sure that somehow it remains symmetric. You can also show that this formula preserves positive definiteness, but the formula just actually chooses this bk times sk, and then the same transposed. Here's a transpose. The bk I don't need to transpose because it's already symmetric, and I divide this by sk transpose bk sk, that's just a number. And then I add at the end a yk times yk transpose divided by sk transpose yk, which is again a number, so that's why I can really divide by it. And if you look at this formula, it's just a formula. The interesting thing I want to point out is that it's these are two vectors basically. I could also write it like this. I just write it differently, bk sk transpose, it's the same, so I just wrote it differently so that my point becomes more clear. This is one vector, this is the same vector transposed, this is a vector, the same vector transposed. And that's the original matrix n by n. So what we do is actually, it's a rank 2 modification because we add one rank 1 matrix here and another rank 1 matrix here. So it's also sometimes called a rank 2 update, because you update your matrix a bit. I mean, n by n is a lot of numbers, right? N times n, and we only change a few directions, so to say, even though we modify each single number. But it's only in a subspace of rank 2, and what we can easily check is actually bk plus 1 times sk. What is it? So does it actually satisfy the second condition? And I just want to do that as an exercise. We multiply it with that bk times sk, that's nice. Here we get something, okay, that is interesting. What we do here is actually, if we multiply this whole matrix with sk, then this term together gives this term, and so they cancel each other, and then we have minus bk sk what remains. And here what we get is actually here, this is multiplied with sk, so this and this cancel, and then we get plus yk. And you see, it's what we wanted to show. The remaining thing that remains is just yk. So it exactly satisfies the second condition. And what we will actually show later is that in some sense, but this is not exactly right, so I should not write it actually, that this bk approach, actually the second derivative of the right solution, at least in the relevant directions. So these methods have actually a nice property, namely they recover the true Hessian at least in the directions where we need that. Yeah? So whenever you have a wrong Hessian, you do a step that is inconsistent with the true Hessian, then you will actually learn from that and you will adapt your Hessian so that it gets this information right. So to bring this back to our example in the Swiss mountains, so assume that you are going and the only thing that you have as knowledge is actually some points, and at these points you have also the gradients. Yeah? And when you have now collected two gradients, then you will actually know that maybe one gradient was going very steep and the other was actually not so steep. Yeah? And you also know the distance that you took between the two, and this will actually help you to build somehow something, to learn something about the quadratic model that should be behind. So you actually try to collect information about the quadratic model of your whole big landscape by these updates. What is nice about them, why they are so popular, is you don't need anything you don't need second derivatives. So you only actually have to, what you need to do in a Newton type method anyway is you need to evaluate your gradient. Yeah? So gradients you need. And once you have a gradient, you can also remember a gradient. I mean, you have the new gradient, you remember the old gradient, you take the difference, and then you can actually already update your new Hessian matrix based on that. And so with your new gradient and the new Hessian that you got from this formula, you can actually easily compute the new step, xk plus 2, and so on, right? And so you can actually use exactly the same information that you use for the steepest descent method. Yeah? So this needs only gradients. It's only gradients, so that's good. But this also only needs gradients. So it's the same. So it has the same things that you need per iteration, but it gives you at the end faster convergence, and that's why people use this a lot. The last of the methods that I wanted to mention are inexact Newton method, but I don't have much space, so I just mention them here. C, D, E, inexact Newton method. So it's again something which sounds like quasi-Newton or Newton type, but when people say inexact Newton method, inexact Newton method, what they mean is actually that you somehow have a linear system. You actually look at the perfect Hessian, so you actually solve this system. That was the linear system that you would have to solve in an exact Newton's method, right? So that's just writing this inverse not here but there, because you will actually not compute an inverse. You will have to factorize it. And so the idea of an inexact Newton's method is to solve this system inexactly. For example, with an iterative method by using CG or whatever, or by using an inexact factorization of this matrix, e.g. An inexact factorization. I think we need to talk a bit about linear algebra issues later, but then you actually call this an inexact Newton's method. So just the language. Yeah? So we have Newton type methods is everything. Yeah? I call it Newton type. Yeah? And then there is exact Newton, there is Gauss Newton. I mean, everywhere is Newton in the name, right? Then there is quasi-Newton. That means that somehow you update this Hessian matrix. And then there are also inexact Newton's method, which say you somehow invert the system incompletely, and that you can always interpret as using some matrix BK, but this matrix is not really formed in the inexact Newton's method. It's just some name. Good. In order to prepare ourselves for the next lecture, I need a blank on the blackboard, and I just wanted to already prepare you a bit. The next lecture is after the break, of course, but I wanted to mention that what all these methods do is somehow they look at the beginning, they iterate using some matrix and some gradient, and what they would converge to at the end is actually a point that should satisfy that the gradient is zero. That's a stationary point. That's what we want. And so what I want to point out is that this whole thing, nabla f of x star, is a square system of equations. So it's actually, this nabla f is a map from Rn to Rn. So it is basically a root finding problem, and I want to mention this, and I mentioned it already, because the next chapter I decided that I would be completely in the root finding chapter setting, and I will just regard any function from Rn to Rn, and I will, for a moment, for the next hour, actually we will forget about the fact that we want to find a root of the gradient, and I just want to say we want to find some root of some nonlinear function, and we will use inexact derivatives of this nonlinear function. And later, afterwards, we will do the connection to Newton type optimization again. So I want to look at general convergence results of Newton type methods, and this chapter is not yet in the script but will be in the script soon. Okay, so let's have a 10-minute break until 20 past, please. And as promised, I want to start a new chapter in which I want to look at the general convergence theory of Newton type iterations. Yeah? So this will be called chapter 8. And it is about local convergence of general Newton type iterations. And this is not yet in the script, but it will be soon. So in order to change the language and to make sure that you later can actually transfer any result that we will need to this case, I will say that I have a function f which is mapping from some space Rn to another space Rn. And actually I will call the variable of this function w just to make sure that it's not necessarily x, but it can be of course also the x of the optimization. So it will be some function mapping from w to f of w. And of course it should be a function that is C1. So continuously differentiable, and we will make some more assumptions on it soon. But what you remember, what was Newton's idea? Yeah, so just let's recall it. The aim. Let's first say, what is the aim? Find a w star with f of w star being 0. And this is now a big F, and it's a vector valued function which has exactly the same number of inputs as it has outputs, right? So that is actually the general setting for root finding. And the exact Newton's method, of course, the idea, so you remember that idea, was actually that you just say, okay, let's linearize, and now we actually look at the first order Taylor series, and here we have J, the first, this is WK from now on, right? WK times W minus WK, that should be equal to 0. That will give you the new iteration, and if you resolve this system, you will get the iteration formula WK plus 1. So this is actually the new state, WK plus 1. If you resolve that, then you get the expression WK minus J of WK to the minus 1 times F of WK. Now that is what we call the exact Newton method in the general case, so independent of optimization. That's exact Newton. And then we can, of course, also define the general class of Newton type methods, Newton type iterations, so not necessarily for optimization. And here we call the derivatives, actually we will use an approximate derivative instead of the right one, and we call this M. Also different to what we had before, this B, but just to make a different language. So a general Newton type iteration would actually be replacing this thing with something approximate, namely an M, which could be different in every iteration, could be also the same. Maybe we choose it later. But then the Newton type iterations, they will result in this formula where you will get minus mk to the minus 1 f of wk. With mk invertible, otherwise we couldn't write this thing. And of course somehow this mk should be similar, but it will not be equal to the Jacobian of f at the point where we are. So that's the general Newton type iteration. So this is the class of methods we want to look at. And I want to start with an example so that we get a simple feeling of what these methods are, right? So let's just make it extremely simple. So I just want to say that my function is a scalar function. And why don't I do something a bit funny. Let me just take w to the power of 16 minus 2. Okay, so it's actually the 16th root of 2 that I want to find with this, and now I could compute j. What will be the j? The j will be 16 times w to the 15, right? I think that's it already. And then, of course, what would be our iteration? wk plus 1 is equal to wk minus, and then we have here j wk to the minus 1 f wk, which is given by wk, and then here we have minus wk to the 16 minus 2 divided by this thing, and that will be 16 w to the 15. Okay? So then we can somehow do our calculations, and if you would start an iteration, you would get, when you initialize close enough to the real solution, you will get very quickly converging to the right solution. Let me illustrate this function a bit. So let me illustrate it here. So the function has a 0 at some point, which is between, I think, 1 and 2. It must be a bit bigger than 1, right? So let's say here is the values of w. Here is 1 and there is 2. And then I have actually at 0, I have the value minus 2. So here I am here. And then my function goes like this. And then, I think I should go a bit quicker. So it goes up. And then it goes very quickly, very high up, right? Because it's w. So this would be f of w for this example. And what would be a Newton type method? A Newton type method would now choose something like a different m in every iteration, which is not necessarily equal Newton type. We choose mk different than j of x, wk. Yeah? And so I want to choose something, and I just want to give you an idea of what we could choose. We could choose, for example, let's say the derivative at this point, just to make it simple, because I can evaluate it quickly. So I could take, for example, I could say mk is equal to j at 1 for all k. So I'm lazy, and I just say I take always the same value, namely j1, and what is it? It could be, I evaluate j at w equals 1, so this point here is actually this derivative, and then I take it, for example, 1 over 16. Sorry, not 1 over 16, 16, right? So 16 would be my possible value that I could take for my m. And now the question is, does this method still converge? And actually we can then write down what our method would be, this inexact method for this example. Yeah. So this is not the only choice, but this is one choice I just make. But then my iteration will be simply given by this thing, and I will have the 1 over 16 here, and then I have wk to the power of 16 minus 2. And now we can actually check if this will converge or not, and you will, we could do this as an experiment if you like. But what you know is that if you have a Newton's method, and if you start close to your solution, and if your derivative is, so to say, is the correct one, that then you get quadratical convergence. But that's something we didn't prove yet, so I just want to say it. But intuitively, it's clear if we have always the right derivative, and we are close here, then actually I cannot distinguish my linear approximation anymore from my true function, and so intuitively it will be very good. While when I use this fixed, so this is mk is always identical to j at 1, so that's like this fixed choice that I make when I'm, for example, here. I will still have this derivative, so it will not necessarily be tangential to the function, and it will give us this solution. And if this m is too different from my true derivative, I will actually diverge. I think in this drawing I would maybe diverge, maybe converge. This is actually something we cannot check by just looking at the graph, but we can check actually by doing this experiment. But the intuition is that we will actually solve a nonlinear root finding problem with something which is not tangential, like in the real Newton's method, but which is approximately tangential, right? So that's the general idea of a Newton type method. And so now the intuition is, of course, that it would work well, and that's what I said before, works well if mk is similar to j of x, wk, right? So that's, I think, what we said already. And now we want to establish some little conditions on this. And these conditions I want to form in form of a simple theorem that we can easily prove also. And this theorem comes now. And this is actually what we call the local contraction theorem. And I will have, I will have to make two conditions for making sure that this converges. And the two conditions one of them is actually that the m should not be too different from this, and the second one is actually that the j itself should not be too different at different places. Okay, so let me just state this theorem. Wk converges to W star with contraction rate. And now I write a contraction rate, which is actually this thing, Wk plus 1 minus W star, is smaller than, and now I have some long term and some short term, Wk minus W star. So it's something like a linear contraction, but let me put this rate here, and afterwards the conditions, right? Here will be a kappa, I call this thing kappa, plus omega half plus times Wk times W star. So I have a contraction rate where this is, so to say, the linear contraction factor, which itself depends on the distance itself. Under some conditions, and these conditions are if W0 minus W star, so if the initial value was smaller than, and I think here I should take already slightly tighter result than what I have here. Here's 1 minus kappa divided by omega, so that's the same kappa and omega, yeah? But I didn't define kappa and omega yet. Yeah? If the first guess is close enough to your solution, yeah? W0 close enough to W star, W star being a solution, right? And now come the crucial things where the omega and the kappa are used. We will have two conditions, namely that first of all the j itself should be not too different from another j. So what I will actually assume is that the j at 2 points, so the linearization itself should be bounded. And it should be bounded by something that is actually this rate omega. And I will, and it should be small when my distance between 2 points is small, and I will need it actually only for points where one of them is an iteration point, the other thing should be any arbitrary point. And I will state this a bit differently because I want to rescale these things. So before I take this difference, or after I take this difference, I multiply it with a symmetric matrix, namely with the same iteration matrix, and then I put a matrix norm around it. And this is a statement which is basically a Lipschitz constant on the derivatives. Yeah? So that's but it's a different formulation. It's a Lipschitz condition on J. So this should hold for all W and all K, yeah? So all iterations K and all W. Basically, if it would hold for all two values of W, then it would hold also for those values which are actually visited in your iteration. And then there is a second condition, which I will write in the same way. And the second condition is actually a bound on the distance of this M and the J, and I will use the same strange form of norm. And the strange form of norm is actually allowing me to get this unitless again. I will. So this is an affine invariant formulation of the Lipschitz constants. But let me just state it. So I take this strange weighting again, and here I put now the difference of J WK minus MK. Yeah, that's what I want and what I need, and I want to bound this thing and make it smaller than kappa K, and that should be smaller than kappa, and that is smaller than 1. Okay, so I have a sequence kappa K that should be bounded above by a constant which is definitely smaller than 1. Yeah, and actually I should have here index K, then my theorem will be a bit more general and I will prove it this way. Yeah? So for all W, yeah, and for all indices K. Actually I could also say for all WK. Yeah? Yeah, actually the iteration is defined by that formula, right? Maybe I should first, before I continue, I should actually make sure that we are right. So WK plus 1 is always generated by WK minus MK to the minus 1 F of WK. So that's like understood here in this theorem. I should maybe say this, right, where this holds. And also what we have is F of W star should be a root. So otherwise this theorem is incompletely stated. Yeah, so we have this iteration, and of course we start at W0. So W0 is something you start, and once you put it in, yeah, for example, in our example here, we could just start with 1, yeah, for example, and then we start and we get this point as the next solution, then we go up, we get then this point as the next solution, and then we get this one, and here actually I think it will diverge in this plot. So we will easily diverge. But these are conditions which say when it will converge, and these conditions I want to use and to use in a proof in a minute. They actually establish a contraction result, so this distance of a new point is actually closer than the distance of an old point by a factor, this factor actually, if the conditions are met, and the conditions are first this one, so maybe I should make surroundings around them. So first of all we need to be close to the solution, and this is based on this kappa and omega. Yeah. And I should also, first of all, above this I should say if they exist. Yeah. Exists actually kappa and omega, yeah, so that all these things hold. So that actually this bound is holding, which is basically a Lipschitz condition, and this one we sometimes call a compatibility condition, so that the Hessian that we, or the Jacobian that we use in our Newton type iteration is not too different from the true Jacobian at this point. And these two conditions we would just postulate, and this one is not really restrictive, I should say, because the omega can be, this is an omega, this is a W, sorry, yeah, so make sure this is the only omega, that's a scalar number, somehow smaller than infinity. So if there exist kappa smaller than 1 and omega smaller than infinity. These are the two things that we need, that these two constants exist. And here I repeat this condition that the kappa should be smaller than 1 to be a bit redundant. And in order to be a bit refined, I have here kappa with an index k, which can be even smaller, and that will help me to recover cases where we might get superlinear convergence. What I want to note here, before I do the proof, is that what would be the kappa for exact Newtons, for the exact Newtons method. Just so that we get the... What would be the kappa? So this is a kappa, it's not a k. Kappa I try to draw more curly. So for an exact Newtons method, what value of kappa can I choose? Always? No, not 1? 0, exactly. So it's the best possible value because this and this will be the same, so there will be 0. So for an exact Newton's method, I will have kappa equals 0, and if I have kappa equals 0, then also all these kappa k's will be 0, and then this whole thing will vanish, and I see immediately that I get, so to say, quadratic convergence from this theorem. Yeah? But I get more, and it's a bit more general, and that's why I chose this quite generic framework. And I want to do a proof, which is using these conditions, and which is relatively straightforward using basic analysis tools. And I should say that this is just one version of a theorem that was proven in different contexts by different people. I think Kantorowicz was the first to prove it, but there is also versions by Teufelhardt, for example. There's a nice book on Newton method. There is also Bock, who is my PhD supervisor. And there are different variants of this theorem, and this variant that I present is just the simplest one that I could come up with. It makes a few, it's a two-liner, so to say. I mean, these will be two very long lines, but we can prove it in a few minutes, and we can still have a good understanding of these assumptions. So the assumptions will be slightly different, but usually people use omega and kappa for the two variables, so it's also useful. So let me do a proof. I think we still have 10 minutes. I think we might be able to get to that point. So let me just expand the distance of wk minus w star. And to expand this distance, I will use the definition of my step. So what I will get is actually wk minus mk to the minus 1 times f of wk. And then I subtract here minus I will use also the fact that I have 0 here. Yeah, so this is now a definition, and now I would have to subtract, minus w star, right? This is everything, just a definition, but I will go on and I create a bit of space, so I go here. And I will now put the first two terms to the front. And this one I will actually expand by just saying it's minus mk to the minus 1, and here I put an fwk, and I subtract from it 0, but 0 in the form of this. So I just take this here, just adding 0, right? So this is first trick, because this will allow me to use a mean value theorems. So the other trick is that I will multiply this with a unit matrix, and the unit matrix will be actually this one. So that's a unit matrix, right? So I just put that in front of this whole thing, and then I get here wk minus w star. So I didn't change anything on the first term. For the second term, I now use an integral representation by integrating from this point to that point and using integrating along the Jacobian. So what I do here is actually mk to the minus 1. Then I take an integral from 0 to 1. In order to get that vector, I start, so to say, at the beginning, and I end at the end. So I will actually integrate over j, starting at w star, then I go t wk minus w star, So then I have all these Jacobians, and of course I need to multiply this with the direction in which I go. So I have here wk minus w star and dt. So this is just replacing this this expression here by an integral using basic calculus. And now I could try to somehow multiply some things out. And what I will actually do is let me think of what I will do. I use the fact that I have here already wk minus w star, and here I have the same, right? So what I will now do is I will actually make a distance, I will introduce something with a negative, namely the true j at the point wk, I will subtract it here. So let me do it on the next blackboard, because there I have more space. So I will go on here. So I have mk to the minus 1. And now I do a change at the beginning, and I will also do the same change at the end. So here I have now mk, and I want to multiply this whole thing with wk minus w star. But I say I modify this by just having here the wk. I just subtract this whole thing here. This is the only modification to that term until now. And then I go on by, here's a minus sign. Here's a minus sign. So I will actually, with another minus sign, I will introduce that term here into this integral, so that it's the same term as here. So I will have here actually mk to the minus 1. And then the integral from 0 to 1. And here I had j, and I just copy the things, t wk minus w star. This is the thing that I originally had, and then this whole thing will be multiplied with wk minus w star times dt. That was what we had. But now I want to subtract exactly this thing here. And because I have this already, I have it here, I will just make brackets around it and subtract here the j of wk. And I make the brackets closed. So you see that, I mean, this is trivial because I integrate over something which is constant. This is constant, this is constant. So integrating over it from 0 to 1 will just give me exactly the same value. So what I get here is exactly with the m to the minus 1, with a minus, so with a j, with this thing, and then integrated from 0 to 1 will just give me the same value. So that's equivalent to the term that I just added here. So I just moved it in between these two terms, and now I have nearly everything that I need, because I have now something which is a distance between the true and the other one, and here I have already a distance between 2 times j. So that's what I need, and now let me go on by looking at the norm. So now I take the norms on both sides, and by taking the norm I can now use my inequalities. So maybe I should first say I want to split it into these two parts, so I will just take the norm. I just want to make sure that I don't, this is a bit too fast, maybe I do one step in between. And the step in between is that I take here mk to the minus 1 times mk minus j wk. And I pull this out. It's not necessary, but I do it. So the first term here is already this thing. So now I've taken the norm of the first term, and then I take the norm of the second term. So now I'm here. The minus sign doesn't matter. And I take mk to the minus 1, and then here I have, okay. Here I pull actually the thing, the integral I can pull out, right? So I could actually take here 0 to 1. I pull this into the integral, and then I take the norm in the integral already, and then here I have actually j of w star plus t wk minus w star minus j of wk. And I take the norm of this because that's something I can bound later, right? And then I multiply this. This is dt, and then I pull out this whole norm here at the end, wk minus w star. So until now, I hope you agree. I just took the norm of everything, and I used the fact. I would have compatible metrics and vector norms. So now I can use my bounds, and my bounds will be, here I have a bound that's given by the kappa condition, right? So here I can actually say this is smaller than kappa k times wk minus w star. And now the second term I will still write as an integral, but I will use the fact that I have here already, I know the distance between this and this. I mean, the distance here is actually, this is wk, this is w star, but I can actually see that the distance is 1 minus t. So when the t is 0, I will be actually at w star. When the t is 1, I will be actually at wk, and there is no distance, right? So actually I can take 1 minus t times omega. That's the distance that I get here. And then this whole thing is multiplied with, so the distance between these 2 points is what I have here. So the distance here is wk minus w star. So that's still in the integral, but this is now a constant because I pulled out the length of this vector, which is 1 minus t times this distance. So the distance of this point with respect to that point is actually 1 minus t times the distance between the two vectors. And then I have to multiply this whole thing with wk minus w star. And now I'm nearly ready. I mean, now everything is, this is a constant, this is a constant. I need to just evaluate the integral. Maybe I just do it here. 0, 1, 1 minus t dt. What is it? It's actually, if you draw this function, it's easiest maybe. It's this thing, right? So it's going from 1 to 0, and you see that it's 1/2. And that is the simple integral that we needed here. And then we can go on, and we have that this whole thing, now I don't simplify anymore, the whole thing that I had until now is actually equal to, and I collect now everything, this is kappa k plus, and here I said this whole integral is actually omega half, and then I have once this and once this, but it is also once here, so I will put 1 here, wk minus w star. I make brackets around it, and now I say wk minus w star. So now I have the contraction inequality proven. This is the main thing that I wanted. So you see that this new distance is bounded by the old distance. So that is already this big result here, the one that we really wanted to have. And the rest is following from some, maybe I should say what is the remainder. What we need is actually, if we start close enough, here should be actually a smaller than, I should say, this is exactly smaller. So if our W0 minus W star is smaller than this quantity, then this whole thing, let me just say, if W star minus W star, W0 minus W star is smaller than 2, let me just see, 1 minus kappa divided by omega, that will imply, if we just plug this in at this first term, then you see that actually this is, this 2 and the omega will just be cancelled at the first term, right? And then we have 1 minus kappa, and there is a kappa, this is smaller than kappa, that means that actually kappa 0 plus omega half W0 minus W star is already smaller than 1. That's actually the same. I could even, but that's an implication because I use kappa 0 here. But because kappa 0 is actually smaller than kappa, then this whole thing will be smaller than 1. And that means that already the first iteration, if you go, this will imply that the distance W1 minus W star is also smaller than, it's actually evens, it's exactly smaller than W0 minus W star. And you see that it's already smaller, and that means that the same argument can be done again and again and again. Yeah? And the contraction rate will be valid, so I mean you really converge, and this inequality will hold, and you have convergence. Yeah? So this inequality alone would not be sufficient if you're not close enough, because these terms might actually blow up, and that's exactly the reason why Newton's method can diverge. So you see two conditions which are necessary in practice. One is really binding that we have a sufficiently close approximation. The second one is that we need to be sufficiently close to the solution. And this one I don't think is really binding, because when you can always make it true by starting close enough to your solution, if your MK is correct enough. Okay, so that was a fast and rough way to prove this local contraction theorem, but I wanted to prove it in this general form, so that we are, whenever we find a Newton type method for anything in this course, we can refer to this theory. Okay? That's it for today. I am looking forward to see you on Friday.